All right, good morning, everybody. My name's Martin Atkins. I'm here with you again for a webinar on industrial process heat. And what we're going to talk about today is really an introduction to process heat and some of the concepts which we will build upon in later webinars, especially to look at, I guess, the demand side of process heat. And in the future, James Neal here will be giving webinars on steam systems and sort of the supply side of things. So just a reminder, once again, this is being recorded, this webinar, and will be available for download. ICA has kindly sponsored these. There's also if you go to YouTube and search ICA Business, there is a YouTube channel where the last couple of webinars are available to watch, and this one will be loaded up over the next few days on there as well. Okay. So please feel free to shoot through any questions, and we'll deal with them as we go, or we might leave them to the end. We'll just see how we go. So what I'm going to talk about today, this is a bit of an outline, is obviously talk about what process heat is and some of the definitions that people use. Then I'm going to talk about demand and supply, two aspects of process heat. We'll talk about what a hot stream and a cold stream are, and talk about demand reduction versus increased heat recovery. And then we'll go through the brief overview of demand side assessment, how to look at potential reduction opportunities, and where to from here. Okay, so what is process heat? So typically industrial energy use is around 30% or about a third of a country's total energy use, and that's fairly typical depending on which country you're in. It does vary a little bit, but in New Zealand it's about 30% of our total energy is used by industry. And depending on the industry, the mix between thermal energy and electrical energy does vary. Obviously, if you're into aluminium smelting, you have a lot higher electrical demand, but typically the rule of thumb for most general processing industries is about sort of 2/3 of your energy is thermal and about a third is electrical. Typically though, your thermal energy is used, your fuel is fossil fuel based, coal, natural gas, maybe heavy fuel oil, something like that. Although some industries do use a lot of wood and biomass. So obviously the wood processing industry, sawmillers, pulp and paper, they tend to use a lot of wood and biomass, and so that's sort of a special case, but generally our thermal energy comes from fossil fuels. In New Zealand though, there are some areas which use a high level of geothermal for process heat. So over in Kawerau, for example, there's a large industrial cluster there which use a lot of geothermal heat for process heat, so direct use is what we call that. There are a few other places in the North Island that use geothermal heat for kiln drying of timber, but yeah, that's usually not an option. It's very location specific, obviously. Okay, so when we talk about process heat, I guess there's a wide definition which we tend to use here. Is it's really any thermal energy demand. So that includes both heating and cooling. Okay, so but there's also a narrow definition which typically people at industry have in mind when you say process heat. They think of heating only. Okay, and I'm going to focus a little bit more on the narrow definition about heating, providing heat to the process today, but in some cases we'll talk about cooling as well. Now we are going to have future webinars that address the cooling aspect of it. I think the next webinar that we have in a few weeks will be an introduction to process cooling, but we're going to talk about some of these concepts today around what is process heat and go from there. Okay, so typically you can divide industrial heat demand into 3 temperature levels: low temperature, medium temperature, and high temperature. And some of the temperatures are a little bit fuzzy around what's low and what's high. It can be industry specific, but typically anything below about 100 degrees Celsius we consider low temperature. So things like space heating, washing, hot water, things like that, that typically is demand in that low temperature range. When we get into processes such as evaporation and drying, for example, we're in the medium temperature range, which is typically between about 100 to 400 degrees Celsius, and then anything above around 400 degrees, we're into the high temperature range. So processes like metals, ceramics, glass, things like that tend to have a lot more demand at the high temperature range. And so your process may have a mix. You may have some low temperature demand and some medium temperature demand. It really depends on what process you have and the split between them. So to give you an idea, this is some data from Europe, from the EU. And what this shows on the left here, we have the total amount of energy being used. Okay, so the total PJs or petajoules, and then we have different industries down the bottom. And the red bar, or the red part of the bar, is how much demand is at high temperatures. The I guess it's orange is in the medium temperature range, and the yellow is the low temperature. So for example, if we just look at basic metals, okay, we have about 90% of their demand is in the high temperature range, whereas if you go to food and tobacco, it's about an even split between in the medium temperature and the low temperature range. Okay, so you can see that the demand, whether it's high, medium, or low temperature, is very much affected by the type of process or industry that you are looking at. Okay, and in New Zealand, obviously, these 3 that I've highlighted tend to be the bulk of our process heat demand. Food, processing, dairy would fit into that, pulp and paper, and then basic metals. And so even though our demand will be somewhat less than in Europe, it gives you an idea of the relative proportions of the demand at these different temperature levels. Okay, so we're going to spend a bit of time talking about supply and demand and where our process demand comes from. So if we just consider a company for example, okay, we may have a number of different processes, and it's important to think about the process heat demand and supply as 2 separate things, and we're going to talk about that now. So in our company, we may have a number of processes or sub-processes. Okay, so this is parts of the process where we do something, okay? And there will be obviously some heat demand and cooling demand in each one of these processes. And then in order to supply that heating and that cooling requirement to those processes, we will have a utility system which provides those utilities, both heating and cooling, and that provides those to each of the processes. Okay, and so if we look at this a different way, we have our demand. So our heat demand is driven by the process that we have. We have a supply that then provides that utility to those processes, and then we have a distribution system in order to distribute the utilities to to the processes and supply and satisfy the demand. And so it's important when considering energy reduction that just to keep in mind that the demand is driven by the process. Now, obviously, there's some things we can do on the supply side to improve the efficiency of the supply, but if we don't address the demand side well, then what happens is we end up wasting energy more efficiently, I guess, is one way to put it. But really, it's important to first start with the demand side and then have the supply side match the demand in the most efficient manner. And the distribution of those becomes important as well, especially when we're talking about steam systems and things like that. Okay, so if we just focus in on the demand side a little bit more, here is an example process. Okay, we have something going on in a reactor, and then we have a separator which is separating out our product, and there's a bit of a recycle as well. Now, if we just look at this, okay, here we have some steam and some cooling water being supplied to the process in order to satisfy the heating and cooling demand. Okay, so we've got steam in these places here. So this is what we call our utility demand. Okay, we have hot utility in the form of steam in this case, and we have cold utility or cooling utility in the form of cooling water. Okay, that may be some other cooling utility like chilled water or refrigeration or something like that. In this particular case here, we have steam being injected directly into the process stream, and so this is what we call direct use of utility. Okay, so this is an example where you're actually mixing in your utility in order to provide heat. There may be some other process requirement why you need to do that, but that is direct use of utility to provide heat in this case. These other heat exchangers are what we call utility heat exchangers. So these are heat exchangers which then obviously provide utility to the process stream. They may be heat or cooling, it depends on what's required. Okay, so these two up here where we're supplying steam, we usually refer to these as heaters, and the other ones we can sometimes call coolers. Okay, but they're utility heat exchangers. These other two heat exchangers that we have in our process, what they're actually doing is recovering heat from one process stream to another process stream. Okay, so this is providing cooling to one process stream, which is heating another process stream. So we call these recovery heat exchangers because what we're doing is actually recovering heat from a process stream and supplying it to another. So in that case, we're providing both cooling where it's required and heating where it's required. And so what that means is we then don't have to supply hot utility or cold utility to those streams because we're using other process streams in order to accomplish that heating or that cooling. So that's really a brief look at the demand side. If we have a look at our supply side for a moment, this may be a typical steam system where we have a boiler that produces steam. So we burn some fuel in our boiler, we produce steam. We may have a number of steam headers at our plant at different pressures. So in this particular case, we have a HP or high pressure steam header, a medium pressure, and a low pressure steam header. We may have a letdown valve or letdown station. Maybe we have to superheating, maybe we don't. And that is basically to drop the pressure from one steam pressure to another. We may have a steam turbine, so we may have cogeneration. Instead of having a letdown valve, we actually use a steam turbine in this case a back pressure steam turbine, to drop steam from one pressure to another and then generate power within the as part of that letdown, and then before we supply heat to our process. Usually there's some form of condensate return, and so depending on the process and how well our distribution system is managed, we may only return a portion of the steam that we use as condensate. If there may be some direct use, for example, where that's not available to return to the boiler house, and so we then have some make-up water in order to make up the condensate that's not returned. We'll have a deaerator and a feed water pump. So on the supply side, there are a number of elements which are there in order to help provide our process with the heat that we require. And this utility system, they tend to be quite large at large sites because there's actually quite a lot involved in supplying utility to the plant. We may have other configurations. We may have a gas turbine, for example, that produces power, and with that, with the exhaust gases from our gas turbine, we may recover heat from those and generate steam in a heat recovery steam generator, for example, an HRSG. So there are a number of different configurations that we can have for our utility system, and we may have what we call cogeneration or combined heat and power, where we also produce power as part of our utility system. And that power can either be used directly on site, or it may be exported to the grid, or it may just offset what we import from the grid. Okay, so that's just a really brief look at, I guess, the demand and the supply side. And it's important when we think about process heat that we sort of get that clear in our heads, that we have a demand which is driven by the process, and we have a utility system in order to supply that. So we're going to talk a little bit more about demand and how that's driven by the process. So if we go back to our process now that we considered earlier, we have our reactor and our separator, and we had our utility heat exchangers supplying utility. Now if we just consider the process streams for a moment, we can define two types of streams when we consider process heat. We've got what we call a cold stream or a sink, a heat sink, which are streams that need to be heated. Okay, so for example, we may have a stream that comes into the plant at 45 degrees, and before a process we may need to heat that up to 125 degrees. So that is a cold stream, a stream that starts cold and needs to be heated. We also have on our flow sheet, we have hot streams or heat source streams. So these are streams that are hot that need to be cooled. So we may have a stream that comes out of a process at 185 degrees, for example, which needs to be cooled down to ambient conditions, say 20 degrees. So that is a hot stream which requires cooling. And it's important when we look at our process from this point of view that we actually identify which are hot streams and which are cold streams. So if we go back to our flow sheet here, I've just indicated which streams on our flow sheet are actually hot streams and which ones are cold streams. So for example, this stream here, feed A, the main feed coming in, is obviously a cold stream because we're supplying heat both by utility and with this hot stream, this exit from the reactor, we're supplying heat and heating that up before the reactor. This stream which comes out of the reactor obviously comes out hot and needs to be cooled before the separator. So we recover some heat in these two heat exchangers before providing the rest of the cooling at this cooler here with cold utility. This other feed B, where we use our steam directly to heat that, that is also a cold stream because we are supplying steam and heat to it. you'll notice that both the recycle stream over here and this return from the separator are neither a hot or a cold stream. What that indicates, not that those streams don't exist, they do exist, but that there's no heating or cooling requirement for those streams. Okay, so they'll be at a constant temperature, and so they're not a hot stream or a cold stream. Okay. So when we look at our process streams, for each stream we have what we call a supply temperature. Okay, so this will be the temperature which the stream begins at. Okay, and then we have what we call a target temperature, which is the temperature which the stream needs to get to for our process. Okay. The other important characteristics of the stream is what we call, it has to do with the flow rate or the heat capacity flow rate, which is simply the mass flow rate of the stream multiplied by the specific heat of the stream. So for example, if we had a stream that was 6 kilograms per second, and if it's water, so the specific heat of water is 4.8 kilojoules per kilogram per degree C, which we increase it. Okay, so that's the specific heat here. Then our heat capacity flow rate, or our MCP for that particular process stream, will be 25 kilowatts per degree C. So what that tells us about the stream is that for that particular stream and that particular flow rate, that we need to supply 25 kilowatts of heating or cooling in order to change that temperature of that stream 1 degree C. Okay. From that, we can then work out the heat flow or the amount of heating or cooling that we need to supply in order to change the temperature of the stream from the supply temperature to the target temperature. Okay, so this formula here, you just highlight it. Okay, so the heat flow Q is equal to the MCP multiplied by the difference between the target temperature and the supply temperature. So if we go back to our example where we had 6 kilograms per second, we multiply that by the heat capacity, 4.18, and we multiply it by the difference in between our target temperature and our supply temperature. So this example is for the first stream there, and so we need to supply a total of 2006 kilowatts in order to change that temperature from 45 to 125 degrees. The bottom one has an MCP of 40 kilowatts, so per degree C, and so for the bottom stream, we'd need to supply a total of 6,600 kilowatts of cooling in order to reduce the temperature from 185 down to 20 degrees. Okay, so these particular properties are important when we're considering our hot and cold streams. And this is the first three, the supply temperature, the target temperature, and our flow rate, or our heat capacity flow rate. Those are the three minimum pieces of information which we need in order to define our hot and cold streams. Okay, so we're going to go through a bit of an example here of a drying process. Okay, say milk drying. So we have our raw material come in, and we may do some thermal treatment to that, and that's typically in the low temperature range. Before we have some evaporation, okay, so we're removing water in order to increase the concentration before we go into a spray dryer to then dry the product up to the final moisture content. And as we said before, the evaporation and drying process typically occurs at that medium temperature range. And in this case, it's typically between 100 up to about 250. So what we're going to do is just focus in on on one particular stream, okay, this main air to the spray dryer, okay. And if we assume that the air comes from outside, so let's say it's coming in at 15 degrees, so that's obviously the supply temperature, and we need to heat that up to 200 degrees before it goes into the spray dryer, and the amount of air that we need for our dryer is 43.4 tons per hour. So in that particular case, we can apply the formulas that we had before. Okay, the heat capacity, the specific heat capacity of air is about 1.1, 1.2 kilojoules per kilogram per degree C. And so the total that we need to supply is about 2.2 megawatts of heat in order to raise that amount of air from 15 to 200 degrees. Okay, so we're going to look at that particular stream and look at some options that we could supply that heat. So the first thing that we could do is we could just meet all of that demand by using utility, in this particular case steam. So we could heat that whole air stream just using steam. Okay, and if we were using 40 bar steam and we took that back to 99 degrees at 1 bar condensate, then we would need 3.4 tons per hour of steam in order to supply that amount of heat, the 2.2, 2.3 megawatts. Okay, so that's one option. The other option is if we have some other stream that needs to be cooled, maybe a waste stream, for example, then we could supply some of that, or maybe all of that demand with recovered heat. Okay, so here on the right we have some wastewater at 80 degrees and we have a certain volume of that, 10.5 cubic meters per hour, and let's say we reduced that temperature to 35 degrees, okay, then we would be able to recover 548 kilowatts from that wastewater, and that would heat the air from 15 degrees up to 60 degrees. Okay, so there's no problem with that from a temperature point of view, and so what that ends up doing is reducing our steam. It reduces our steam demand by about 0.8 tons per hour, and so we reduce the amount of utility that we actually require. So we'd only have to supply 1720 kilowatts with steam. Okay, so in this case we have a utility demand reduction, meaning the amount of steam that we've used has reduced, but there's no reduction in the process demand. We still supplied all of the 2,268 kilowatts to the air, and so there was no process demand reduction, there was only a utility demand reduction. Now, utilities are what we pay for in our fuel cost, and so often when we talk about opportunities for energy reduction, often we're looking at ways to reduce our utility. Okay. So if we change the utility that we supply, does it reduce demand? Sometimes people say, oh, well, if I change the utility that I use, then I may reduce my demand. So in this particular case, if we just go back and look at supplying all of our heating from 40 bar steam, let's say we instead supplied that with 30 bar steam. Okay, all that has changed is that the temperature of our steam has changed. The amount of energy in our steam doesn't really change much between 40 and 30 bar, so it's about the same amount of steam, and so we still have the same demand from our process, okay, the 2,268 kilowatts, and we've not actually saved any utility. Now there may be a cost differential between our 40 and 30 bar steam, although that's typically not the case here in New Zealand, but I guess the key message is simply changing your utility does not change the demand. Right, so if we just look at what are some ways that we can actually reduce our process demand. Okay, so that's the demand that's driven by the process. So that's the true demand. Okay, originally here we had our inlet air, and to go from 15 to 200 degrees with that amount of air, we needed 2,268 kilowatts. So there's really only two options that we have to reduce the process demand. We can firstly reduce the target temperature. So this is the temperature that we need to get that stream to. Let's say, for example, we had a look and we only needed 180 degree air going into our dryer. Then for the same volume of air, we would only need 2,021 kilowatts. Okay, so if we reduce the target temperature, we will reduce our process demand. Now that may or may not be possible. It really depends on the process. Often when you change temperatures, there are some other effects that go on, such as quality and things like that, yields, for example. But that may be an option. Do you actually need to heat your streams to the temperatures which they are currently being heated to? So that's one option. The other option is to reduce the flow rate or reduce the amount of our process stream. So in this particular case, if we reduced our air volume or mass from 43.4 tons per hour down to 40 tons per hour, but we left the target temperature still at 200, then we would reduce our heat demand to 2,091 kilowatts. Okay, so the other way to reduce the process demand is to reduce the amount of the volume of your process stream. Okay, or you could do these two things together potentially as well. Both reduce the target temperature and reduce the flow rate. So these are the ways to actually reduce the process demand. Now, that may or may not be possible depending on the process, and there's often a lot of work that needs to go in order to actually determine whether this is feasible. Now, you may have other streams. Say, for example, you may have a hot water rinse or hoses or something like that, where that temperature may be a lot more flexible. So you might decide, I'm going to reduce all of our hoses in our plant. Instead of sending 60 degree water, maybe 55 degree water is fine, and we can reduce that set point down, and there'll be a demand reduction that way. Okay, so a little bit of thought has to be put into whether this is actually possible in your particular case. Okay, so we can really bring this and summarize this in two ways. If we want to reduce our utility or our fuel use, there's really only two ways to go about this. One, we either reduce our process demand. So we look at, do we need to supply or do we need to heat the streams to the target temperature, and do we need that amount of volume or mass in our process streams? Okay, so we reduce the process demand, or we can increase the heat recovery. If we increase the heat recovery, then we actually reduce the amount of utility that we need, both heating and cooling, and so we can reduce the amount of our utility demand. Now, if we're looking at reducing cost, which is often the main driver, then there are some other things that we can do to reduce cost, things like fuel switching, for example. We may fuel switch from a more expensive fuel to a cheaper fuel. There are some issues with that sometimes, especially boilers are not as flexible sometimes as what you hope, and so that may or may not be an option. But certainly that is something that can be looked at in some cases to reduce cost. Now, obviously, if you fuel switch, you don't reduce your process demand, and so all you've done is reduced your cost. There are some other issues with fuel switching though, which we won't go into depth, but there can also be an efficiency penalty, I guess, in fuel switching, and then obviously there's some maintenance and reliability issues as well. But maybe we'll have another webinar on fuel switching and I wouldn't say perils, the issues around fuel switching. But that is an option, but there can be some other factors you have to consider. But there's opportunities there that can be looked at. Often you're limited, as we mentioned before, if we look at reducing your process demand, often that can be very limited, and you don't have a lot of room to move to change your process demand by changing your temperatures and your flow rates. And as I said before, there can be other consequences. Maybe there's a yield consequence in some reactor where changing the temperature or the pressure may affect the yield negatively. And so really, and this is really the first thing you begin to look at when you're looking at process heat reduction or demand reduction, is really around how can we increase heat recovery. And so that can be, that is usually the best way to begin, is to look at increased heat recovery, but also ask the question, can we reduce the demand by changing the temperatures? But increased heat recovery is usually the first place to look, although it can be challenging, but there are some methods that can be used. Okay, now for real processes, as I said, process change is difficult and there's some risk involved. In real processes, often you have multiple hot and cold streams. Okay, instead of having just 2 or 3, there may be tens or hundreds of hot and cold streams in your process. At real processes, you also have multiple utilities. So you may have different steam levels, you may have hot water, you may have different cold utilities as well, cooling tower water, chilled water, and they often have very differential cost differentials as well. So for example, the cost differential between chilled water and cooling tower water is more than an order of magnitude, and so if you're using chilled water to provide cooling when a cooling tower would do, then you may be spending more money on utility than you need to be. Also, you may have direct heating going on as well, and so real processes tend to be a bit more complex in the use of the utilities. And then the other thing you need to consider is that you have existing heat exchangers in place. So you have both process-to-process exchangers that are recovering heat, and then you also have utility-to-process or utility heat exchangers which are supplying utilities to the process. So the question is, how do you go about systematically looking at demand reduction in a real life process? And so from a demand point of view, what you're looking at is looking at the heat exchanger network. What does the network of heat exchangers actually look like? And so as we said before, we have 2 main classes of heat exchangers. We have process-to-process heat exchangers. So these are heat exchangers which have process streams on both the hot and the cold side. So they're cooling one process stream by heating another. And we have our utility heat exchangers, our heaters and our coolers. And so, as we said before, we have a number of hot streams in our process and a number of cold streams. And really the network, the heat exchanger network, is the structure or the network of heat exchangers which are providing heating and cooling and also recovering heat. So one of the ways which we show this so we can actually understand it a little bit better is by what we call a grid diagram. Okay, and there's no real set convention on how to draw these, but typically you have your hot streams on the top, and they may go from left to right or right to left, and then you have your cold streams on the bottom. And then what you do, okay, is you indicate your process to process heat exchangers with this this coupling here. Okay, so so this is one heat exchanger, which is with this top hot stream and this cold stream here. Okay, so that indicates a recovery heat exchanger between those two streams. And we then have our heaters and our coolers supplying utility to the process. So you can see here that with our process heat exchangers, so if we just pick on this one again, we just remark it. This hot stream is being cooled by this other cold stream here. And so this is where we have heat recovery, and this is a really good way to reduce our utility demand, is to recover as much heat from our hot streams and supply that to our cold streams as is feasibly and economically possible. So in our demand side assessment, what we're really trying to do is to determine what the maximum amount of heat recovery is that we can get, and there's a thermodynamic limit to that. And then how do we go about and design or modify our existing heat exchanger network in an economic way in order to get closer to that target or to that minimum. And so this is sort of the process that one might go through in order to perform a demand side assessment. Okay, and they can be sort of divided up into four main parts. So the first part is what we often call process demand mapping. And what this involves is really coming up with a mass and energy balance of the process. Okay, so looking at the temperatures, the flow rates, how much heat and how much cooling is being supplied. So having a good mass and energy balance of the process is important, and then extracting the important data with regards to hot and cold streams from that mass and energy balance. Okay, so that really maps the demand side of the process. And then the next step is really around what we call benchmarking and targeting. So there are a number of techniques which are available in order to calculate what the minimum amount of hot and cold utilities that we need to supply to the process based on our hot and cold streams. Okay, and that's a rigorous target that can be calculated, and what we can then do is benchmark our current utility use against both that hot and cold utility target. And that really gives you a potential amount of savings that could be realized. It may not be economic to realize all of those savings, but at least it gives you a guideline as to what is possible. Also within that exercise, and we're not going to go through how to do that today, but you also can focus in on individual utilities. So for example, you may come up with a minimum amount of chilled water that you need to supply to the process. And so not only do you get an overall hot and cold utility target, but you can also get a individual utility target and look, if I've got a really expensive utility such as chilled water, then I can see how much potential reduction I have for that particular utility. So that's what we call the benchmarking and targeting stage. The next stage is really looking at the heat exchanger network, the current network that we have, and what modifications can be made in order to get closer to our target. Okay, and there's some formal methods in order to do that, but we're really looking at adding in new heat exchangers, potentially making heat exchangers larger, or changing matches between hot and cold streams. Maybe if we, instead of having stream A on the hot side, if we had stream B on the hot side, we may take better advantage of some temperature or some flow rate, something like that. So that's really around looking at what modifications can we do to the network in order to realize some savings. And remember, we're not necessarily reducing the process demand, we're only looking at recovering more heat in order to reduce our utility demand. And then finally, we will then evaluate a number of different alternatives. Okay, so typically in the heat exchanger network analysis stage, you may have multiple options, and so then you need to evaluate those in terms of how technically are they technically a good fit for your process, and what are the other implications, say from a control point of view, of having that solution, and also the economics is looking at what are the relative economics between the different alternatives, and then putting together recommendations and then hopefully implementing something. And so really the center of this demand side assessment is what one of the main techniques to do and perform this analysis is what we call pinch analysis. Now we've done this, we've talked about this in the past a few years ago in our previous webinars, and we're not going to go into the details today, but pinch analysis or heat integration is a well-established method that looks at how do you reduce your utility demand in an industrial process. Okay, and there are a number of what we call graphical methods in order to look at what our hot and cold streams are and how much heat recovery there is between them. And so we have our composite curve on the left there and our grand composite curve on the right, and they become quite useful in looking at what the potential heat recovery and what the minimum hot and cold utility requirements are for a process. And then from that as a basis, once we've established those targets, we can then look at what our current heat exchanger network may look like. There are some techniques to look at which individual heat exchangers are the most likely candidates for change or increasing the utility use unnecessarily. And so there's some formal methods around that, which is the wider pinch analysis technique. And so in the future, we're going to go through what some of these techniques are. It may not be necessarily that you use them yourself, but you may have a consultant come in and perform this on your site, and at least you'll know what they're doing and be able to ask them some good questions. Okay, so where to go for some additional information. Today's really just been an introduction, talking about demand and supply side. As I said, in the future, James Neal is going to be giving some webinars on steam systems in particular, so looking a little bit more closely at the supply and the distribution side. The next webinar we have Dr. James Carson from the University of Waikato here. He will be talking about process cooling. There is an audit standard that was developed a few years ago that looks at how to audit process heat systems, and it talks about both demand and supply sides of the equation. And so the link is there. If you go to the EMANS website, that is available to download at no charge. There is also American Society of Mechanical Engineers. They have two relevant standards, one around assessments on process heating systems, things like furnaces, things like that, and there is another separate standard for steam systems. Okay, and there's the names of those two standards. Once again, the ASME standards, there is a charge to get those, and I think it is fairly substantial in order to get a copy of that. But they are available there if people wish to go and look at those further. Okay, so where to from here? As I said just previously, in 2 weeks' time, on the 11th of November, Dr. James Carson will be giving a webinar on industrial process cooling. Later in November, James will be giving one on steam system efficiency, and then compressed air later in December on the 9th of December. Okay, so you can register for all of those webinars at our website, energyefficiency.nz.com, and once again, reminders and invitations will be sent out as well. Also, don't forget about ECA's business program. Obviously, if you have any more questions or comments, please feel free to contact us directly or to get in touch with ECA and contact your ECA account manager. And just the final reminder before we take questions that these are available for viewing. I think ECA is setting up something on their website to view them from their website directly, but they also have a YouTube channel. If you search ECA Business, the webinars will be posted there, and the last 2 webinars are available there already to watch. All right, so thank you for your participation. We have a few minutes for questions, so please feel free to fire any questions through that you may have, and we'll answer them.
Just as we're waiting, just want to take a minute to thank Martin for his time today, and just to remind you all that the presentation today will be available for free download via a link off our website, or you can go direct to the ECA Business YouTube channel. Yeah, so we'll give you guys a couple more minutes if anyone has any questions to fire them through. No, and we'll close up if we don't have any questions. All right, thanks very much, Pat. All right, hey, thanks very much, guys. If you do have any further questions, feel free to email either Martin or myself. And just a reminder that you can register online via our website, energyefficiency.nz.com, under the webinar tab for the future webinars. Thanks very much, and we'll see you in a couple of